Hello, I am José Soler, and I will introduce a miscellany of theoretical concepts and more practical issues on the Siesta code. Siesta was designed to be a standard DFT code specialized in fast calculations for large systems, but also allowing highly accurate calculations. It uses norm-conserving pseudopotentials, a basis of numerical atomic orbitals, a uniform space grid for some integrals, and an order n functional for solving Schrödinger's equation. Let us start with the very basics that probably most of you already know, but that I will introduce for completeness. First principles methods intend to predict the properties of molecules and materials, starting from just Schrödinger's equation to describe the evolution of the system, and Coulomb's law to describe the interaction between the particles. The first basic approximation is Born-Oppenheimer's. Although all the particles in the system move simultaneously, influencing each other, the nuclei are much heavier than the electrons. This means first that their wave packets are very narrow and can be approximated by a point charge. And second, generally the nuclei move much more slowly than the electrons, giving the latter time to adapt to their movement and stay in their ground state. So what we can do is, at each particular time, consider the nuclei at fixed positions, and then solve Schrödinger's equation for the electrons. Through the charge distribution of the electrons, we can find the electrostatic forces on the nuclei and find their movement, most frequently by classical Newton dynamics. This decouples the motion of electrons and nuclei and greatly simplifies the problem. The next basic step is density functional theory. Even if we consider the nuclei as classical point charges at fixed positions, the interaction between the different electrons is a correlated motion, which implies that we have to deal with a wave function, which is a function of all the electron positions together. And this makes the problem very difficult to solve. What DFT does is to replace this n-electron problem by an effective one-electron problem in which each electron moves independently in the mean field or in an effective potential created by the nuclei, the potential created by the electron charge, the electrostatic potential, and an extra term which is called the exchange and correlation potential, which accounts for the complicated correlation effects. What this allows is to decouple the motions of the different particles and to replace the n-electron problem by a one-electron problem, which in turn allows to write the n-electron wave function by a product of one-electron wave functions. Still, the exchange and correlation potential that one electron at point R fills is a function of the density of at all other points. So it is a function of an infinite number of variables. In practice, one substitutes this complicated function by a much simpler approximation. The simplest of one is the local density approximation. In this, we make the exchange and correlation potential depend on the density at only the point at which the electron is. To calculate this potential, what we do is to assume that we have a system of constant density equal to the density at that point, but constant, and then we calculate the so-called exchange and correlation hole that the electron forms by depleting the probability of finding other electrons nearby using quantum Monte Carlo methods, which are very accurate. This exchange and correlation whole has two parts. The first one is due to the Pauli exclusion principle, which implies that where one electron is, there can be no other electrons, and which in reality implies that they cannot be there nearby. And this part is called the exchange. And another part which is due to the repulsion, to the electrostatic repulsion between the electrons, which is called correlation properly. In the generalized gradient approximation, the potential depends not only on the density at that point, but also of the gradient of the density at that point. So it is a two-variable function. In the non-local van der Waals exchange and correlation functionals, the potential depends on the density at 2 points simultaneously and their gradients. The normal implementation of density functional theory is the Constant method. You start with an approximate density, usually a sum of atomic densities, and you calculate an effective potential made by the electrostatic potential produced by the nuclei and the electron density, and you add the exchange and correlation potential. You then solve Schrödinger's equation by expanding the wave functions in a basis set, what reduces the differential Schrödinger equation to a matrix eigenvalue problem. Finally, you find a new density as the sum of the occupied electron wave functions, and you repeat this self-consistency cycle until the density no longer changes. It is easy to see that the constant method scales computationally as the cube of the number of electrons. And this is essentially due to the Pauli exclusion principle that requires that the occupied states are mutually orthogonal. Thus, simply to check that they are in fact orthogonal, you have to perform an integral over all space whose volume is proportional to the size of the system, so to the number of electrons, and you have to do this for each pair of occupied states, psi I and psi j. So this gives the three factors n that make the cos scale as n cube. However, although the Bloch states, or the molecular orbitals of the system, that is the solution of Schrödinger's equation, are extended over all space, one can perform a unitary transformation of them to make them as localized as possible. And these are called the Vanier functions. That means that their overlap will be substantial or non-negligible over with respect to a finite set of other Vanier functions around each other. And furthermore, the integral to compute their overlap will have to be performed only over a small region of space which does not scale as the system size. And that means that all the problem of orthogonalizing the Vanier functions will scale as n instead of n cubed. And this is basically taking advantage of the principle of localization. To expand these localized Vanier wave functions, or in general any electron wave functions, localized or not, Siesta uses a linear combination of basis orbitals, which are also strictly localized within some radius that will be different for each basis orbital. I will not say anything more about basis orbitals because there will be another talk about them, except for a couple of details. First, that the basis orbitals are the product of a radial function times real spherical harmonics. Then the m quantum number is no longer the true angular momentum, but it is just an index going also from minus L to plus L, but which gives some order of the spherical harmonics, which is somewhat non-standard. And the second detail I want to mention is that Siesta always writes a file called the name of the system .orb index with all kinds of details about the basis orbitals, like the atom to which it belongs, the species of that atom, the index of the orbital within its atom, its quantum numbers, its symmetry, and other details. In this figure and table, we compare the performance of the Siesta atomic orbitals with that of a plane wave basis. The curve shows the convergence of the total energy of bulk silicon as a function of the plane wave cutoff using a plane wave basis. The arrows show the energy of Siesta using different basis sets. So you can see that a single zeta basis with just 4 orbitals per atom is equivalent in energy convergence to a plane wave basis set with about 50 or more orbitals. And a standard double zeta plus polarization basis set of Siesta is equivalent in terms of energy convergence to a plane wave basis of more than 200 orbitals. As I mentioned before, the differential Schrödinger equation can be reduced by a normal algebraic equation involving two matrices and a set of expansion coefficients of the wave functions in terms of a set of basis orbitals phi. The two functions involved are the matrix elements between the basis orbitals of the Hamiltonian operator and the overlap between the basis orbitals. In the pseudopotential approximation used by Siesta, the total Hamiltonian is composed by the Laplacian operator T, the pseudopotential, which describes the interaction with the nuclei and the core electrons, the Hartree electrostatic potential produced by the valence electrons only, and the exchange and correlation potential that depends on the valence electron density also. The pseudopotential operator is in turn composed by two terms. Local pseudopotential that goes as the valence charge of the atom over R at long distances, but which is it has some different shape at short distances, and a non-local Kleinman-Bylander operator, which is a sum of projections over orbitals also centered on the atom, which are somewhat similar to the basis orbitals, but with a different radial shape. For computational convenience, in Siesta, we handle the long-range potentials produced by the nuclei and its cores and the electron valence density by introducing a density which is the sum of the atomic densities, and creating a new potential as the sum of the local part of the pseudopotentials and this potential created by the sum of atomic charges. And this potential is called the neutral atom potential. And the potential created by the difference between the true density and the sum of atom density. As a result, the total Hamiltonian is the sum of these 5 terms. 2 of them can be handled by two-center integrals, and the remaining 3 terms are performed as an integral in a uniform grid of points in real space. The two-center integrals are performed very efficiently using the convolution theorem. Thus, the overlap between 2 orbitals phi1 and phi2, separated by a distance r, can be described as the convolution between the 2 functions phi1 and phi2. And the convolution theorem says that a convolution in real space is the same as a normal product in reciprocal space. So all we have to do is to Fourier transform the basis orbitals to reciprocal space, multiply them, and then Fourier transform back the product to real space. And this will give us the overlap at all distances r. This is done once for all and stored as a function of r. The terms of the Hamiltonian that depend on potentials, electrostatic or exchange and correlation potentials, are performed in a grid of mesh points in real space. We start by calculating the so-called density matrix from the expansion coefficients of the occupied electron wave functions in terms of the basis orbitals. Then we can find the density at every grid point as a product of pairs of basis orbitals times the density matrix elements. Once we have the density at every grid point, we can calculate the exchange and correlation potential and also the electrostatic potential produced by delta rho, the difference between the density and the sum of atoms, using fast Fourier transform methods